So, hi and welcome to the lecture. I just saw that we could make this a little bit brighter here. Okay. So I don't have any questions for the last lecture. So we talked about the proximal point method, which is a theoretical method to solve convex optimization problems. We will come to that. We'll come back to the proximal point method later in the lecture when it comes to monotone operators. Then it will be we'll turn that method into something particularly useful. But before we come to that, there's one important thing we need to talk about when it comes to convex functions, and this is the notion of convex conjugation. There's Okay, so lecture 13 is about convex conjugation. So that's the notion of duality for convex functions, which is kind of related to the notion of duality for convex sets, which we could characterize from the inside and from the outside. From the inside by doing convex combinations, and from the outside by dealing with all separating hyperplanes, or hyperplanes which are such that the convex sets lies totally in one half of the of these corresponding half spaces. Okay, and without further ado, just let's write it down. Okay, so here's the definition. 13.1. So if f is a convex function, no, it's actually any function from Rd to the extended real numbers, then the conjugate, or sometimes called Fenchel conjugate, is denoted by f star. Let's say it's it's also a function from Rd to the extended real line, and is defined by taking the supremum over all x of inner product p with x minus f of x. So that's the definition. And so somehow this can be seen. There is a graphical interpretation, but I always get it wrong. So I could try to draw a picture because it's kind of related to supporting supporting affine functions, But I usually get this image wrong when I try to show it. So what could be interesting here, or what one could note here, is that the conjugate is kind of defined in terms of slopes. So the x's are the points in Rd, but also every point in Rd can be interpreted as a slope. The slope of that function p times x. That's a linear function on Rd and has gradient p. So this is the function of slopes. This notion that these variables p correspond to slopes, whereas the points x correspond to points in the Rd. Okay, so that is the conjugate. It's of the same type here. And of course, as you probably all, I don't know if you think about it during the lecture, but in this case it's very simple to just replace Rd by any Hilbert space. Again, we just need real valuedness here, or extended real valuedness, and inner products. If Rd would be any Hilbert space, the notion here would be exactly the same. Even if there would be a Banach space, then this would be the dual pairing with the dual space, but we don't talk about that here. Okay, so and moreover, we could also do this twice, and this is then called the biconjugate. The biconjugate is f gets 2 stars, and I plug in an x again, and this is then supreme over all p, inner product again p with x minus f star of p. So it's totally symmetric. We just do it twice, and then we get the biconjugate. Okay, so first a few quick observations. So this function here as a function of p, so the function inside the supremum as a function of p, it's affine, and affine functions are convex and lower semi-continuous. And this is a supremum over a bunch of convex and lower semi-continuous functions. Okay, so f star is convex and lower semi-continuous. And note that this is totally independent of any properties of f. Right? As soon as f is just any function, this is convex and lower semi-continuous. And f by conjugate f star star as well. So that's important to note. So f star, and of course then f star as well, is always convex and lower semi-continuous, no matter what f. Okay, so here let's first do, before we come to more theory, let's first do a few examples. Okay, so here's the first one. We do one-dimensional examples. Higher dimensions are of course also possible, but let's do just one dimensions for now. Let's take alpha times x squared. For alpha non-zero and positive, this is a convex function, and so let's just try to calculate the conjugate. So we need to find that p times x minus alpha x squared. This is what we need to calculate. So this is just one-dimensional analysis. So what is the maximal value this function can assume? Okay, so this you want to find where this is maximal. Yeah, what you do when you want to find out where something is maximal, we calculate the derivative, set it to 0, solve, and plug it in. So the derivative of this with respect to x is just p minus 2 alpha x equals 0. So that's the derivative of this. P minus 2 alpha x has to be 0. Okay, what does that give? This gives us x is equal to p over 2 alpha. Okay, so we plug it in here. It's then p times p. Also, and we don't have to worry if it's a minimum or a maximum. Of course, it's because this is here. It's linear minus convex, so it's concave. So it has each local maximum is also it's well global, and so if we would have had multiple solutions here, all of them would be equally good. So okay, we don't have to worry about that. So just plug it in. P times p over 2 alpha minus alpha times p squared over 4 alpha squared, and this gives us another p squared. This gives us a p squared. Oops. Oh, there's another typo here I didn't catch. So this here is 1 over 2 alpha times p squared, and this is minus this 1 alpha cancels. It's 1 over 4 alpha times p squared, so it's 1 over 2 alpha minus 1 over 4 alpha. It's 1 over 4 alpha times p squared. Okay, that's it. So if you do that again, what's the biconjugate? F2 star of x. Of course, you can basically do just the same argument as here, or you could just say what comes out if you replace alpha by 1 over 4 alpha. And if you do that and do the math, you get back this is actually alpha times x squared, which is again f of x. Okay, that's interesting. The biconjugate is the function itself. Okay, and we will see sometimes, this is not always the case, but in this case it can be characterized, and we will do that. Okay, another thing is it's also probably interesting that if you take alpha equals 1 over 2, then 1 over 4 alpha is also 1 over 2, which means that the conjugate of for f of x is x squared over 2. It holds that the conjugate of x is f of x. And so here we kind of misuse the variables because you plug a point into a function which would like to take slopes, but it's possible because it's both vectors in Rd. So this is one thing we're going to characterize. When does that hold? And we're also going to characterize this. When is the conjugate equal to the function? And it turns out that this is basically the case for only one function, and this holds for a very broad class of functions. We come to that. So here's another example. What about f of x is the exponential function e to the x? Okay, so what we need to do here, we need to consider the function p times x minus e to the x and see where its supremum is. Okay, and we do a case distinction for if p is negative, then this has a downward slope and goes to infinity for x going to negative infinity, and this goes to 0. So we see that, let's call this thing here, I don't know, let's call it just probably h of x. Then h is unbounded from above. It goes to plus infinity if x goes to negative infinity. So this shows us already that f star of p is plus infinity for p negative. Okay, what happens for p equals 0? For p equals 0, we need, we only have the function if h of x is then minus e to the x, and this is not unbounded from above anymore and has, it doesn't have a maximum, but the supremum is at 0. So this shows that f star of 0 is 0, because this is bounded from above by 0 and it gets arbitrarily close. Okay, and so for the last case, which is p positive, what do we get there? So then we have the function, so h of x is then px minus e to the x again, and it's bounded from above again. So this is now, it has positive slope, but we subtract something which goes to infinity. So as the larger the x, this goes to negative infinity fairly quickly, this goes to plus infinity fairly slowly, so this is going to win, and we expect that this has one global maximum. Of course it has one global maximum because it's continuous, and this goes to minus infinity for x to infinity, this goes to minus infinity for x to negative infinity. Okay, so let's calculate the derivative, which gives p minus e to the x, and this has to be 0, and we're going to solve that. X equals to the logarithm of p, and plug that in. So we have the f star of p is, this has to be plugged into the function h, which is p times logarithm of p minus e to the log of p, which is exactly p times log p minus p. So, and this is the conjugate for positive p, for negative. So in total, it looks like I forgot. So you may note that this p times log p is the entropy function. You probably heard of the entropy in different contexts, and this minus p, it's just tilting it by something. But it's still, what is also interesting is that if you send p to 0, then of course this goes to 0, this goes to negative infinity, this goes to 0, but p log p goes to 0 from below. So at least in 0 the function looks like this. And then here it jumps up to plus infinity. It's just locally around 0, and I'm not really sure what's happening up here, so I think this grows like p a little faster than p something, I don't know. Okay. So, and then again, you may verify by direct computation if you do the biconjugate. So take the conjugate of this function f star, which you get like by these three inequalities, you will see that you get f back. You get back the exponential function. Probably just do that for training. Okay, let's do something non-smooth. So f of x is the absolute value of x. So then f star of p is equal to the supremum of p times x minus absolute value of x over all x. So then in the lecture notes I wrote by direct inspection, and that's basically all I can say about it. But let's draw a picture. So this function here is just that, minus absolute value of x. And what we do, if we add px to that, we just tilt it around, right? If we just add something like that, it means that this gets like this, and probably like that. So if we add, maybe I should have used color. So if you add the green, which is this here, to the black, then for the full thing we would get something like this here. We tilt it around. So. And then you see, if the p is small enough, this function always is below the x-axis and has a supremum at 0. But as soon as the slope of p is larger, the p is larger than 1, this here tilts above the x-axis and it gets unbounded. So this is the direct inspection that I was talking about, and what we're going to see is we get infinity or 0, nothing else is possible, and we get infinity as soon as the absolute value of p is larger than 1, and we get 0 as long as the absolute value of p is smaller than 1. That might happen, so but it's still a convex lower semi-continuous function, and so that's how it is. So this is actually the indicator function of the closed interval from -1 to 1. And this is now, yeah, this is not f, okay, but anyway, okay, this is not what I wanted to say, but what is also true, if you calculate the biconjugate of that, you will get f back. Okay. So this has all been convex functions, actually convex lower semi-continuous function. Let's do a non-convex example. F of x maybe infinity if x is larger than 1 by magnitude, or 1 minus x squared if x squared is small equals to 1. So this function looks like, if here's -1 and here's 1, it jumps up to plus infinity here and there, and here it's kind of a negative parabola or something like that. So this is the epigraph here. And epigraph not convex, function not convex. Okay, so what is f star of p? And I don't think I have any calculations in the handout, but let's do on the lecture notes, let's just do it here. So what it is, it's taking the supremum over all x over p times x minus f of x. And so if we have minus f of x here, but f is it's plus infinity at some points, we just need to consider these points. Because if we subtract infinity here, this is always negative infinity, this can't be so supreme. Okay, so we only consider the cases where we subtract something finite. So here. Okay, good. And hopefully I did that right, but I guess I did. Okay, so now let's calculate where the supremum lies. Probably it's a bit complicated because of these edge cases, but anyway. So let's see, let's take the derivative, and then after that consider the edges. The derivative would be p, this goes away, it's plus x squared equals 0. Okay, and we need to solve that. It's plus x squared. So of course not. It's plus 2x. Sorry. And this gives us x is equal to minus p over 2. Let's plug it in. So and then we need to check, is this is it between -1 and 1? So this is minus p over 2 is between -1 and 1 if and only if p is smaller than 2, which kind of surprises me here. I'm pretty sure what's the outcome, but I never did the calculation like that, so I'm a bit confused right now what's going to happen. Maybe I'll check this out in the break and show you the calculation before I get stuck here too much. Okay. I check this out in the break and come back to that. Sorry. So okay, that has been examples. Now let's prove some things here. So, and the most interesting thing would be that the biconjugate, so that we can recover the function from its conjugate under some circumstances. So before I come to that, which is not totally straightforward to prove, we first prove the simple things. So if we have two functions f and g from Rd to the extended real line, then we always have if f is larger than g, then the conjugate is smaller than the conjugate. So this is kind of order reversing. Then if we have 2 points in Rd, and f or f, the conjugate, one of them is finite, then we always have that the function plus the conjugate function is larger or equal to the inner product. And this is so-called Fenchel's inequality. You're going to use that a lot, Fenchel's inequality. So you probably know that this incorporates one inequality which you're probably familiar with. If we take our example 1, so 13.1, with this f, f is alpha x squared and the conjugate is 1 over 4 alpha p squared. This shows you that alpha x squared plus 1 over 4 alpha p squared is larger or equal to xp, which is the version of Young's inequality. Usually Young's inequality is maybe maybe Young's inequality is often stated with alpha over 2 here, and then you would get 1 over 2 alpha here. This is the standard way to write Young's inequality, but that's it. Okay, and for every x and its conjugate, you get this another type of these inequalities, and you get other familiar inequalities like this. For example, you may also know about Young's inequality with p and q exponents here. So p is now taken. So, but with conjugate exponents from functional analysis, you also get that from this general fact of Fenchel's inequality. Okay, but there's more. This is the second property. The third property that's kind of amazing is we have the fact that conjugation is kind of related to subgradients, and it says that if p is a subgradient of f at x, this holds if and only if f of x plus f star of p is equal to the inner product. So as soon as we have equality in Fenchel's inequality, we have the subgradient inclusion here. We know that this is a subgradient of that. And because this here is totally symmetric, we also get that this is the case if and only if x is a subgradient of the conjugate at p. Okay. And that's now, I find this pretty amazing. So this fact here is called Fenchel's equality. Equality, and the fact that p is in the subgradient of f at x is if and only if x is the subgradient of the conjugate. It's called subgradient inversion theorem. Yeah, because well, we're going to talk about this also when you come to monotone operators. The subgradient can be considered as a set-valued map, or a multi-valued map, because for every x you get a set of subgradients, possibly only containing one element, possibly containing a lot of elements. But anyway, you can always consider it as a set. And set-valued mappings can be inverted fairly easily by just flipping the graph. We're going to talk about this in detail. But once we figure that out, how to deal with set-valued map, this basically says that the inverse of the subgradient is in fact the subgradient of the conjugate. This is basically what this says here. Okay, this is a totally different form than we are used to. There's nothing similar to this in standard analysis, where you could, what is 1 over the gradient? Doesn't make even sense. It's totally unclear when it makes sense and how we should deal with that. But this convex conjugation shows you the right thing here. And the fourth point is that the biconjugate is always below the function. And this is only an intermediate result. We will show something much better in the following. Okay, let's prove it. Okay, so the first point, let f be larger than g, and then just write down what is g star of p. So write it down, it's the supremum of p times x minus g of x. Yeah, and then it's fairly simple now. We just make what's below the supremum smaller by subtracting more. And subtracting more, we could, for example, subtract f. Supremum of x, px minus f of x. That's less because f is larger than g. And this is exactly the conjugate of f at p. Okay, that is direct. This is kind of very simple. So these Fenchel inequality here, as I said, we're going to use it a lot, and it is powerful, but it's totally trivial because f star of p is defined as the supremum over px minus f of x. So for any x we're going to take, so now I got a mismatch. Let's do it over x bar, 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 and then we just plug in one of these x, any x. We could plug in any x, and it's always, the supremum is always larger. And that's already it. So it's totally trivial. It's just a definition of the conjugate. Okay. So what about subgradient inversion? Subgradient inversion. So what p is in subgradient of f at x if and only if for all y we have, let's write it down first as we used to, f of y is larger or equal f of x plus p times y minus x. Okay, we rearrange that a little bit into the form, so we're gonna bring basically everything to the other side, more or less, except for p times y. So we bring negative p times x to the other side, it's p times x. We subtract f of x, then it's on the left hand side, then this is the larger part. And on the right hand side we have left p times y, and we subtract f of y. Okay. And now we can take the supremum over p, over y on the right hand side, and this shows you p times x minus f of x is larger or equal to the supremum over y over p times y minus f of y, and observe that this here is exactly the conjugate of f at p. And this shows you that p times x is larger or equal f of x plus f star of p, and we also we just bring f of x to the other side, but this is Fenchel's inequality, so we have equality, and actually the argument works both ways. So if we start with f star, it's like this. It works both ways. So if you have equality here, you plug in the definition of the conjugate. You end up here by taking a particular point y. You end up there. So it holds for every y. You end up there, and you get C, it's the subgradient. And so this shows this equivalence, and this equivalence is the same, but just with the roles of f star x and p swapped. Okay, so that is again fairly quick. It's basically just rearranging the subgradient inequality to that, and that's the crucial part you need to observe. And for the last part, this is also very quick. So the biconjugate of x is the supremum of px minus f star of p, and by Fenchel's inequality we know that this is smaller or equal to f of x. And this is then independent of p, so we take the supremum over p here, so and then supremum of p just goes away, and that's basically already it. Okay, good. It seems like a pretty quick. So these are simple facts about the conjugate. What we're going to show next is, so we already know that the conjugate is always convex and lower semi-continuous. What we don't know yet is what happens if f itself is convex and lower semi-continuous, or does it even help? And we'll come to that in the next. First there's a lemma, and then there's a big theorem, the Fenchel-Moreau theorem, which really actually characterizes when the function is equal to its biconjugate. Okay, we'll come to that after the break, so we are pretty quick. Break already starts right now, and so there's 2 minutes of jokes. I hope I can figure out the example here and then come back to that. Okay, so here I'm back, and actually I figured it out. Yeah, and the point was I got confused by not checking if it's a local minimum or maximum. So the non-convex example goes like this. So this is again example 13.2, fourth point. F of x was the function infinity or 1 minus x squared. So, and it looked like that. That was the function. And so what about, so the conjugate f star of p is then the supremum over px minus this here 1 minus x squared, as long as p is not larger than 1. And so just, I think here it's simpler to do graphical inspection. So which means that this function, the negative here, we just flip that around and we get a function like this. So this is minus 1 minus x squared. This is a subgraph. And now if we now add a linear term here, this is going to be tilted a little bit like this or like that. But what I calculated before by setting the derivatives to 0 at this point was this local minimum over here, and I don't want to know that. But by direct inspection, it's pretty clear that the largest point which we get if we add the green and the black, it's exactly here at the right hand side at x equals 1. Because otherwise, if we add these two functions larger than x, we always get minus infinity, smaller than minus, larger than 1, we get negative infinity, smaller than minus 1, we get negative infinity. And the largest value we get is either here or there, depending if p goes like this or p goes like that. So, and so if p is larger than 0, we'll get the value of p times 1, which is p. And if p is smaller than 0, we get the value of p times minus 1, which is minus p. And for p equals 0, you get 0, and both points here are equally good. So that is what you get, and this is exactly the absolute value of p. So the conjugate of that function here is the absolute value, and we already know that if we do the biconjugate, then it's the conjugate of the absolute value, and this is the indicator function of the closed interval. And this is notably not the same as f of x. So maybe if I draw it again, if you use 1 and minus 1, and we get this function like that here. So this is our f, but the f biconjugate is equal to 0 here. And you probably note that this is the convex hull of f. Okay, and this is what we're going to see that this is true in general. Okay, that was the example. Luckily I could fix it, and now we come to the last two big results for the lecture today. So we had that and that. So first there's another lemma, which is not so interesting in and of itself, but anyway, good to know. So we have f is from Rd to R bar, and so then we need to deal a little bit with the edge cases if f is not proper and stuff like that. What can happen in these cases? So if f is not proper, which means either it takes the value negative infinity somewhere or the value plus infinity everywhere, then the conjugate only has two possibilities. Then the conjugate is either constant plus infinity or constant negative infinity. So these non-proper functions f have really not interesting conjugates, I'd say. Second is, if f is proper, then f, the conjugate, is not equal to minus infinity everywhere. It has to be positive, not positive, it has to be kind of larger than minus infinity somewhere. And probably the third part is the most interesting. If f is proper and convex, then f star is again proper. We don't know that here actually, right? The f star could still be plus a constant plus infinity. Two more facts. The one fact is that f star, the conjugate of f, is actually equal to the conjugate of the closure of f. So taking first the convex and lower semi-continuous hull or envelope, and then doing the conjugate doesn't change anything. And now comes the most amazing fact, but actually the proof of this is not part of this lemma here. I'm going to show, so I write it in parentheses here, and also it holds that the biconjugate actually equals to the closure of f. So what we've seen in the previous example with the conjugate of this function, which goes like this, that the biconjugate gives you the lower semi-continuous and convex hull. This is actually true in general, even on Rd, and is also true on Hilbert spaces actually. Okay, we're going to prove the theorem up to here, and then this will be a very short corollary of this thing here and the next big theorem. Okay, let's prove. So first case. So let f be non-proper, and then we have two possibilities. The first case is f of x0 equals negative infinity for some x0. But then the supremum of px minus f of x is always plus infinity, because we can always have the case x is equals x0, then we add plus infinity, and then that's it. This is for all p, and this gives you f conjugate is constant plus infinity. Second case is that f is constant plus infinity. Then this px minus f of x is constant minus infinity, and this shows that the conjugate is constant minus infinity. So these are the trivial edge cases, and so usually these are totally irrelevant in practice, I'd say. I never had to care about these in my entire life, except for preparing lectures like that. Okay, so what is let f be proper? So let f be proper. Okay, and then assume that the conjugate at some point p0 is minus negative, is minus infinity for some p0. But then what we get there, we get that for all x, we would have that minus infinity would be larger or equal to p0 times x minus f of x. Yeah, because the supremum over this is that. Yeah, the supremum over this is that, and if we plug any x in, we still have an inequality. But what we see here is this can be rearranged. If we add add f of x and subtract infinity, this implies actually that f of x is larger equals x, and this not x for larger equals infinity for all x, and then it's not proper. So kind of we prove the contraposition. If the conjugate is negative infinity at some point, then f is constant plus infinity everywhere, so it's not proper. I.e. f not proper. Okay, that was that. Okay, and now do third point. If f is proper and convex, then f star is proper, and also convex. We know that because f star is always convex and lower semi-continuous. First, so show that f star proper. And this is basically an old result already, and this is proposition 5.4, which means that below every convex function there's some affine function, and as soon as we have one affine function there, this defines the slope which lies below, and this gives the finite value. So finite value for the conjugate. Proposition, so there is some p0 in Rd and alpha in R such that f of x is larger equal to p. Oh, there's a 0 missing here. There's a 0 missing. p0 times x plus alpha for all x, and now this shows that the conjugate at p0 is actually bounded from above by minus alpha. Yeah, so you subtract f of x over here, subtract alpha over there, and take the supremum over x on the right hand side, and then gives you that. And this shows that f is proper. F star is proper, sorry. That was the first part. Second part, that f star equals to the conjugate of the closure. So we already know f is proper. F star is proper. No, since f, sorry. So since f is proper, it's enough to show that the convex closure leads to the same conjugate here, and we need lemma, the previous lemma 13.3, the first point. We know that the closure is below the function because it's the largest convex function below, and this shows us that so if we do the conjugate, the inequality reverses, so the conjugate of the closure is larger equal to the conjugate. Okay, also no, this is not the convex, it's the lower semi-continuous envelope, sorry, it's the lower semi-continuous envelope here. But anyway, it's below the function, and then conjugation reverses, so we only need to show the reverse inequality here. Okay, so for the reverse inequality, consider this. The lower semi-continuous envelope at some x0, which is actually equal to the limit inferior of f of x for x goes to x0. So that is lower semi-continuous envelope. That's kind of the definition of that. Then we do Fenkel's inequality. And plug in that f of x, so of course first we copy the limit inferior here, and we replace f of x by some p with x0 with x, p with x minus f conjugate of p. So here's an x and then x0. Fenkel's inequality. But now this here is actually continuous in x, and we can pass to the limit inside, which is then p times x0 minus f star of p. Okay, and we're almost done. This shows us, so just kind of bringing these to the other sides, these two terms, it shows us that f star of p is larger equal to p x0 minus f conjugate of x0. So and what is left is to take the supremum over x0 on the right hand side. Then so the left hand side stays, inequality stays of course, but the supremum over x0 on the right hand side gives us the convex conjugate of that function at that point, which is actually f lower semi-continuous envelope conjugated at p, and this is the reverse inequality. So we have this is larger than f star, but it's also smaller, so we have equality, and that was that. Okay, good. So and maybe I first write down the next theorem, and then show you how this theorem would then imply this fact here, and then prove the theorem. So the last theorem is kind of a major result, 13.5, and this is the so-called Fenchel-Moreau theorem. Okay, and this says the proper f of Rd to R, this is convex and lower semi-continuous if and only if f by conjugate equals f. So that's the simple conjugation result. So the function is equal to its biconjugate if and only if it's proper convex and lower semi-continuous. Okay, so this explains what we've seen in the examples in the beginning, because well we had we always observed that in the case of proper convex and lower semi-continuous function, and the only case we did not observe this, we had that the function was not convex. Okay, so first maybe formulate this as a corollary from this theorem and the lemma 13.4 is that f star is equal to the closure of f if f proper and convex. Now convex would not make any sense. Yeah, if f is proper, that's enough. Okay, and this follows very simple. We have that, so the biconjugate is equal to the conjugate of the conjugate, and the third point of the previous lemma showed us that the conjugate of f is the same as the conjugate of the closure. Okay, and so this is the biconjugate of the closure of f, but this here now is convex and lower semi-continuous. And then by Fenchel-Moreau. This shows us that this is the closure FF. And this is what we wanted to show. Okay, so we also have that fact that if we do the biconjugate, we get the convex and lower semi-continuous envelope of a function. Okay, it remains to prove Fenchel-Moreau. Okay, and this is now a little bit of work, but so nothing so special that we haven't done it before. Yeah, we need to use convexity and lower semi-continuity at some places, and you will probably note how we're going to do that. So first is that this direction here is clear, because if f is equal to the biconjugate, f is especially a conjugate of something, namely of the conjugate, and conjugates are always convex in LSC. Clear, since f star is equal to f star star, hence f convex and lower semi-continuous, and proper we've seen in the previous lemma. So this is the only thing which is interesting here, that convexity and lower semi-continuity imply actually the equality. But then again, we already know something. We already know that the biconjugate is below f, and so we need to show that it's also above f. That's all we need to know. Okay, and how to do that to that end? So we can prove that by proving the following claim. We show that if f of x is larger, strictly larger than some alpha for some x and alpha, then we also have that the biconjugate of x is larger equal to alpha. So we want to lose the strict inequality, but of course this doesn't matter at all. Yeah, so if we have that, then we are done. And this probably goes, this goes actually, it's then pretty clear, right? If this holds, then f star has to also be larger equal to f. So for example, if x is not in the domain, you could make alpha arbitrarily large. You can have alpha arbitrarily large here, and f star is also plus infinity. Okay, but if this is finite and this would not be fulfilled, you could kind of subtract an epsilon from f of f and would still get f star star. But if you then take the half difference between f of x and f of x minus epsilon, you could make f2 star smaller than that and get a contradiction here. That's totally straightforward. So this, if you've shown that, then you've shown that. Okay, let's prove the claim here. Let's prove this. So assume that f of x is larger than x. F of x is larger than alpha. So that means that then x alpha is not in the epigraph of f. And again, in all the cases it gets complicated in convex analysis. You need to use separation theorems. And so here now we have that APF is convex and closed because the function is convex and lower semi-continuous, and this is actually where you also already need it. So we can separate. Separate x alpha from the epigraph of f, and this means that there exists a tuple of p and a. It's rd times r, and an epsilon non-negative such that the supremum of the vector p and a with all the y's and beta, and the y and beta come from the epigraph. This is smaller or equal to the inner product of p and a with x and alpha minus epsilon. So that's the separation of the point x alpha. This is an alpha here. That's an a. That's the strict separation of x alpha from the epigraph. That this here is always on that side of the hyperplane here. So in other words, whenever we have y and beta in the epigraph of f, then we just write this here out. This is then here, this is two inner product, is p with y plus a times alpha, and this is smaller equal than p with x plus oh no, this has been a with beta, sorry. On the left hand side we have a times beta, and right we have a times alpha minus epsilon. And now comes some things you already know. This alpha can be positive, a can be positive. So if a would be positive, you would have a contradiction, because then yb is in the epigraph, which means you can make b arbitrarily large. You can make the left hand side arbitrarily large, but the right hand side is a fixed value. This is a contradiction. So by beta goes to infinity. This can work, because then the left hand side goes to infinity for beta to infinity, but can't be because it's bounded. Okay. Okay, so that was that step. So we have the case a is smaller equal 0. Okay. Yeah, so then we consider two cases. First, if a is really negative. Then we're going to use this inequality here. Is it still visible? Yes, there it is. And divide. So divide this star inequality by minus a, which is then positive. And this is always the case where I get confused, because so but now we divide by minus alpha, that's positive, so the inequality stays the same, and we get what do we get by minus? So I divide by minus a, we get minus p over a times y minus beta, but it's still smaller equal to minus p over a times x minus alpha plus epsilon over a. And we're going to set this value to p bar. And we observe that this is also p bar. Okay. So this holds for all y and beta which are in the epigraph, so we can use beta equal to f of y. This is valid because the pair is then part of the epigraph. And then we get here, this is then p bar times y minus f of y is smaller equal p bar times x minus alpha plus epsilon over a. So this holds still for all y, so it still holds if we take the supremum over y. And if this is a supremum over y, the left hand side here is actually f star of p bar. Okay, yeah, then we get that. So what does that mean? So we can rearrange a little bit by bringing alpha to the left hand side and have alpha a smaller alpha smaller equal, but you could also we get a strict inequality here by omitting the positive the negative epsilon over a term, which we still add here, and get that this is strictly smaller than p bar times x minus f star of p bar. Okay, but this here is to take the supremum over this over p bar would give f the conjugate of f star at x. So this is actually f, the biconjugate of f of x is actually an upper bound. Okay, so this is Fenchel inequality. Okay, and that is what we wanted to show. The biconjugate is larger than alpha, because this is actually we even get strictly larger here. Strictly larger comes from that fact here. Okay, good. This is for the case A is equal 0. Then we have this desired inequality, and you see that f star of x is actually f of x, which is that one want to show. And the remaining case alpha equals 0. It's actually a little bit simpler. Not so okay. If a is equal 0, then this star inequality which we used here turns into just p times y smaller equals p times x minus epsilon for all y in the domain of f, and yeah, that's it. And beta, but beta doesn't appear anymore. Okay, so then if x would be in the domain of f, then we get a contradiction here from that, because we could also use y equals x, and then we would have p times x is smaller p times x minus epsilon, which is obviously wrong because epsilon is positive. So this can't be true. So this alpha 0 does not occur if x is in the domain. Okay. So hence, if alpha is equal to 0, we have necessarily that f of x is plus infinity. In this case we started with. But again, plus infinity, yeah. Okay. Okay. And so now we're going to use Fentel's inequality again. And it looks with different variables. Q times y minus f of y is smaller equal f star of q. And then we combine this with this inequality here. So taking this inequality, multiplying by some mu, which is positive, and adding this to this inequality. What do we get? We get, if we multiply this by mu and add to that, we get y. Oh no, I put it as in the lecture notes. It's then q plus mu times p with y minus f of y is smaller equal to, and we do the same thing here. It's f star of q plus mu times p with x minus mu times epsilon. And so now the interesting thing is that so this still holds for all y and q. So we take the supremum over y on the left hand side and see that this is exactly f star of q plus mu times p, which is then smaller equal times f star of q plus mu p x minus mu epsilon. Okay, we rearrange this again a little bit in the following way. We bring f star of q to the left hand side and f star of q plus mu p to the right hand side, and here we want to have a q times x for reasons which become clear in a second. So this stays here, so we added q times x, and then this gives us here a q plus mu times p with x, and we still have this minus mu epsilon, but we just omit that. Yeah, we just omit that, it's still true. Okay, but here on the right hand side, by again Fentel's inequality, this is smaller equal than f by conjugate of x. We need that term actually. Sorry, we need that, and we put it here. We put it plus mu epsilon here. And this is what we use now, because now we can make the left hand side arbitrarily large by sending mu to plus infinity. So the left-hand side goes to infinity from u to infinity. And this shows us that f by conjugate of x is equal to plus infinity. And this is the same value of f of x. Okay, so maybe we should go over the proof once again, because let's see how it works, because these kind of arguments are sometimes confusing for the beginner and convex numbers, and actually I have to admit it's still a little bit confusing to me here. So what we want to show is that the biconjugate is equal to f if the function is convex and lower semi-continuous. The other direction is clear by what we've seen before. So we already know that the inequality, that the left-hand side here is smaller than the right-hand side, so we only need to show the other inequality. For the other inequality, we show some replacement, saying that if we are larger than some alpha with the function, then the biconjugate is larger than the same alpha, which then says that this has to be at least as large as the right-hand side here. Okay. And now then the thing is, if you start with a point like that, f is larger than f of x is larger than alpha, this x alpha is not in the epigraph, so we can separate it. So maybe I could write it. So this will look like this here. We take some point here and then we can separate it. So because this is not in the epigraph, and you already probably see that if the function is, if the point x is, and alpha is such that f of x is plus infinity already, we could also separate by a vertical hyperplane, which corresponds to a equals 0. So okay, this is the main step here, the separation. This is possible because the epigraph is convex and closed here. So strict separation goes like this. Then we have strict separation. We have this epsilon here, which you want to use in the end. And then again, alpha can't be positive. But just can be seen here. In the negative case, if it really is negative, we will get, again, by cleverly dividing here, the kind of back normalizing, we will get this inequality here, which you can take the supremum over, taking the edge case here. So kind of we move this point f, this point here, as we move this point below really towards that here, and observe that we get this inequality as we desired here. And the case a equals 0 corresponds to vertical hyperplanes more, and on more or less it corresponds to vertical hyperplanes. And then by kind of some formal manipulations, we will see that f star also have to be plus infinity right here. Okay, so that was the proof of Fenchel-Moreau, and that was everything I wanted to say about convex conjugation for today. So, and this is lecture 13, which means the next lecture marks the end of the first half of the full lecture. And the next lecture will be conjugation calculus, which just gives you a few results about how conjugation behaves under some simple operations, translating and tilting and stuff like that. And after that, we will do convex duality. So this is convex conjugation for function, and convex duality is a very powerful notion of duality for convex optimization problems. I don't know, if you took optimization already, then you probably already know that for many optimization problems there's a corresponding dual optimization problem, and by magic I would say sometimes the dual is simpler. And moreover, if you solve the dual, it gives you not only hints, but also exact values for the solutions of the primal problem. So we also have primal dual. So this is kind of amazing that this is happening. And kind of, in my mind, this all boils down to the characterization of convexity from the inside and from the outside. Because this is what lies behind the convex conjugation, and convex conjugation is what lies behind convex duality, and convex duality is, as I said, extremely helpful in practice, because everything you know about the dual gives you hints about the primal, and everything you know about the primal gives you hints about the dual, and so they can really, so it looks like out of one problem you make two problems, but because solving two problems is not necessarily harder than solving one problem, because solving the solution part of the dual gives you hints for the primal and vice versa, and so you can kind of sometimes work your way up to the full solution here. We can only develop this into an algorithmic framework, actually also a quite powerful one, in the second half of the lecture. So if you're really interested in doing hands-on solution of practically relevant convex optimization problems, you would need to stay for the second half of the lecture. One more announcement. In lectures, I think starting from lecture 17, starting from lecture 17, for 6 lectures, this course here will be held jointly with a course for master students at 2 mathematical science institutes in Africa, I think in Senegal and Rwanda, I hope you think so, for a special course for them. And this 6 lectures, starting from lecture 17 on, will be on so-called complexity theory for convex optimization. And complexity theory is kind of tries to quantify how hard is a certain class of optimization problems. And how hard means what is the best thing we can hope for any algorithm to perform on any function of that class. And the theory will go like this, that we'll consider different classes of optimization problems and then show that no algorithm can perform better than that on every function of this class, and then also will show that there is an algorithm which can perform almost as good as that. So that we will make the first step into the direction of showing that there are kind of optimal algorithms or almost optimal algorithms for a full problem class of convex optimization problems. This is what we're going to do in the 6 lectures from starting with lecture 17 on. And after that, we will come to this announced monotone operators and stuff like that. Okay, that's it for today. Thanks for listening, and see you again tomorrow when we talk about convex conjugation calculus.